Hello everyone. Hey James, are you able to hear me, guys? You're muted, James.
Oh, no. Hi. Hi, Nimesh.
Yeah, so the voice is clear, right?
Yeah, it's very clear.
Okay, cool. So, um, I just hope my sheet is visible. So, since Amritanshu, like the other PMRFTA, must already have discussed some of the problems uh, that are there in week 2. So what I'll do is I will just cover some of the theory that is already there in the lectures. I will try to add on to that a bit more. Theory about DH conventions. Yeah, James, you can mute now.
Yeah. So one thing, Nimesh,
Yeah.
like there are some problem which I have to solve. Okay. So
Okay.
how is the session going on? Like you 1 hour and me 1 hour, or is it like how the session goes?
I think we can do 1 hour each. Yeah.
Yeah. Okay. Fine.
Yeah. That I mean
Okay.
that would be cool with me. I don't have any issues. So like, do you want to start or should I start?
You can start, and the thing is like, and I think in the previous session, one of the PMR guys said that it was not recorded. Okay, at the session.
Hmm.
So in the end they have a problem. So that's the
Yeah,
thing.
yeah, cool. Because anyways, they are already covering the other problems. So I was planning to start with some theory, right? So
Okay.
I think I'll just cover some
Yeah.
basics of the theory, and then you can cover the problems related to that. That would be great for the students as well.
Yeah, so I'm covering the same problem which was covered in the previous session, okay?
Yeah, sure.
Yeah, because the students won't be repeated, like they can join any other session. Okay, you can start.
Okay. Yeah, so like about the question related to how to watch the old sessions, they are on the YouTube channels, and the links will be provided to you by the PMRF team. So look out for those emails. Okay. Yeah, it will be on the YouTube channels, and the links will be provided by the PMRF team for the recordings. Also, like, does anybody have any doubt till now in week 0 and week 1 lectures or week 2 lectures? Like, week 2, of course, we'll be covering some of the problems and some theory, but anything specific that you want to ask about?
Excuse me, Nimish sir.
Yeah, yeah, Kumar Patnaik.
This is the first time I am attending, so you told somebody will be providing the links, YouTube links. Who will provide? How can I know?
Oh, yeah, if that is the case, then I can provide you the YouTube link. That is because usually the PMRF team has to share the link, but I'll share the link at the end. Just remind me at the end of the session.
No, no, now you are saying, right? Is there any doubts regarding week 0, 1, 2?
Mm-hmm.
This is the first time I am attending, so is there any recap from your side? Is it possible?
A recap would not be possible because see, it's a problem solving session. So,
Yeah, yeah, that's right.
and most of the problems are there from week 2. Most of the,
Yeah,
yeah.
that is the problem.
So in week 1 we just had a recap of theory as well.
Mm.
So of course you can. There is a recording of week 1 as well on that channel. Because for every week we'll be having this session, we'll record it and then we'll upload it. So you can watch the week 1 recording there as well. That is fine, right, Kumar Patnaik?
But of course, if I find the link, it will be better. You are saying you will be uploading somewhere, right?
I will be uploading somewhere. I will
Mm.
share the link at the end of the session or just
Okay, no problem.
after I finish a bit of theory. Okay?
Okay, sir. Thank you.
Okay, cool. So I'm assuming that the rest of you guys do not have any issues with the theory part. And I will just autofocus. Yeah. So what I'll be covering today is a bit of screw theory, right? Screw theory is, in terms of robotics, is our translational plus rotational motion along an axis. Okay. So of course, the translation motion, if, as we had discussed in the previous week, if there is an inertial frame that we call E, okay, and basis vectors are E1, E2, and E3. So if there is an arbitrary axis, let's say we call it N, right, and there is any body, and we translate it along N, and then we rotate it about N, right, and both of these operations we perform successively, right, about the same axis. So that displacement, okay, that the displacement of the successive translation and rotation of this body about this axis N is called a screw displacement. And why I am talking about screw displacements is because DH convention is, or the DH parameters are basically two screw displacements successively. Okay, the DH parameters, they are two translations and two twists basically, right? So they are two screw displacements involved in derivation of DH parameters. Okay, so what's a screw displacement? Translational plus rotation along N successively, right? One after the other. So if we now come to look on to DH notation that I think we had covered in the previous week as well, but we'll do it again. Okay, so yeah, so what we'll do is we'll just define everything again, right? So this is link I minus 1, this is our link I, right? So I'm making them curved just for representation that yes, they can be curved, right? In usual problems you'll find that most of your links are straight lines, okay, links I plus 1. So according to the convention that we were going to use, that is similar to the convention that is there in J.J. Craig, right? We will mark the axis between link I minus 1 and I as, this is joint I, not joint I minus 1, right? Because this is the convention that we had chosen. In the Schilling convention, this is called the joint I minus 1, and the ith joint is between link I and I plus 1, but we are not going to use that convention. Okay, and this is joint I plus 1. Okay, so currently we are just revising how to specify the axes, the local axes at every joint according to DH notation. Okay, we'll come to DH parameters after that. So what do we do then? We assign the z-axis at every joint along this joint axis that we have just specified. Okay, so the z-axis is aligned with the joint axis, right? And it is from link I minus 1 to link I usually, right? And then what we do is we make a common perpendicular between between both of these zi and zi plus 1. Okay, and along this common perpendicular, right, uh, along this common perpendicular is xi. Okay, and the shortest distance between both these joint axes will also be along the common perpendicular, and that we notify as a. Okay, I don't think there should be any trouble till now. Okay, and similarly, starting with link I plus 1 and between the common perpendicular of zi plus 1 and I plus 2. Okay, so there will be some other frame, right? Some dummy frame I'm drawing right now that will help us define xi plus 1. Okay, so that will, I mean, it is not important that this xi is along your link I. What is important is this xi is along the common perpendicular of zi and zi plus 1. Okay, so we had already talked about frame transformations in the previous week, right? It's what we initially started with. How do we transform frames? Okay, so what do we usually do in robotics is we want to know how to shift between different frames. Okay, how to shift quantities between different frames. If there is some point of interest uh, that I can represent in, let's say, frame I minus 1, right? How does that point look when I see it from frame I, right? That is the usual problem. There can be successive transformations also related, that yeah, if there is some, let's say, frame I plus n, any random frame there is, if I can represent a point in that frame, then how does that point look when I see it from, let's say, I plus 1 frame, okay, or ith frame? So for that we need transformation matrices. That you already know that a transformation matrix is defined by a rotation and a translation, right? So what we need is we need the rotation matrix between the two frames and the translation, total translation between the two frames. And we already know that we can compose, okay, transformation matrices, that if I have between from frame 1 to 2, the transformation matrix is T12, okay, and from frame 2 to 3, okay, the transformation matrix is T23, okay, then I can compose them to get transformation matrix between 1 to 3s just by simple multiplication of 2. Okay, why? Because like we have defined a multiplication operation on this set, right? That we also discussed helped us define the SE3 set, right? The special Euclidean group. So R belong to SO3 and T, the complete homogeneous transformation, the general rigid body transformation in this case, belongs to SE3 group. Okay, so all this till now is just what we have learned previously, and I've just revised how we attach axes, joint axes according to the DH notation. Okay, now what will come on to next is DH parameters. Okay, why DH parameters? Because DH parameters help us easily identify these transformation matrices for robots. For which we can identify the DH parameters correctly, then we can write these transformation matrices much easily. Okay, and how do we do that actually? Okay, so I'll first come to DH parameters, then I will discuss how to go from frame I, joint frame I, to joint frame I plus 1. You need to perform two screw displacements that we talked about here, right? That will also clear up the screw displacements a bit for you guys. Then I think we'll move on to James to discuss, let's say, some problems. Okay, so yeah, DH parameters. So there are 4 parameters as has already been discussed, I think, right? So the first one, it's the A, that is the length of the common perpendicular between Zi and Zi plus 1. Okay, and it is called the link length, distance between Zi and Zi plus 1 along xi, right, along the common perpendicular. Yeah, that's what I'm doing actually, Mohit. Is there any specific detail that you want about them, or like this is the exact thing? Like how do we define DH parameters? Yeah, so I had already discussed about DH notation. Okay, how do we assign frames, joint frames according to DH notation? What I am going through right now is how we define DH parameters based on DH notation. Okay, so for DH notation, we just assign the Z axis at the joints, and then we assign the xi along the common perpendicular of both the joints, and the length of this common perpendicular is A. This is the first DH parameter. Okay, and then we have alpha. Okay, alpha is called the joint twist. Okay, and what is alpha? It is the angle between Zi and Zi plus 1 about the same axis xi. Okay, so these are for your first 2 DH parameters, and this is the first set of screw displacements needed to go from joint frame I to joint frame I plus 1. Okay, but we are not there yet. To completely reach or to completely define this transformation, the rest of the 2 parameters are your link offset. Okay, so the link offset is your distance between xi and xi plus 1. Okay, so if I just extend xi here, okay, so this distance between them, right, this is link offset, this is D, and if we can just assign I to all of them. Okay, this is about Zi plus 1. and then the final parameter is joint angle, that is angle between xi and xi plus 1 about zi. Okay, so these are how we define in our convention, that is similar to the convention in JJ Craig, the DH parameters, right? And why do we exactly define them? As I mentioned, to make these transformation matrices, okay, particularly from frame I to I minus 1, okay, to define this basic transformation matrix for any two frames, okay, we take help of these four parameters, okay. And how do we take help of these four parameters? Now, if you see if you take a look at the first set of screw displacements that I talked about, okay. So why I say screw displacement? One correction: this is also about zi. Okay, so this distance is about this axis. Okay, so when I defined screw displacement above, right? So what was a screw displacement? It was a translation and rotation along the same axis successively. Okay, now if we look at the definition of our DH parameters, okay, so this distance is basically a translation along xi, and then this rotation is a, you know, a angular displacement along the same axis along xi. Okay, so this is our this follows the definition of a screw displacement. So this is a screw displacement 1, okay. And these two, okay, so this displacement also, it's a translation from xi to xi plus 1 about zi, and then an angular displacement, okay, or a rotation between from xi and xi plus 1, no, yeah, between xi and xi plus 1 about zi. Okay, so this is screw displacement 2. So when we perform these two in succession, okay, then we get the transformation matrix, or basically that is when we can actually align frame I with frame I plus 1. Okay, we are, if we do all these or both of these screw displacements one after the other for frame I, we would have aligned frame I with frame I plus 1. Okay, like that is the whole idea of getting transformation matrices. Like, how does the origin of one frame look like in the other frame? Okay, so now if we want to write this transformation matrix using our DH parameters, okay, so how do we do that? Okay, so first of all, we know that to go from, you know, frame I to frame I plus 1, okay, we have to perform, let's say we call the first screw displacement SCR1, okay, and then the second one we call SCR2. Okay, so how do we write the, you know, SCR1? Okay, that yeah, that takes everything to I frame, right, from, let's say, the intermediate, I'll call this intermediate frame the M frame, okay, just for the sake of notation, because again, to reach I plus 1 we have to apply SCR2 as well. Okay, so this first screw displacement what was it? It was a translation along, okay, it was a translation along x by, this much amount by AI. So it was translation along AI and no, translation along xi and translation of AI, okay, along xi and rotation of alpha I about the same xi. Okay, so how will the transformation matrix for the first screw displacement look? It will have our fundamental rotation matrix about the x-axis and the angle will be alpha I. Okay, the displacement vector in this case will be, since it is along x, will be AI 0 0 because it is a pure displacement along only x. Okay, it's a pure displacement along x. Then we'll have our constants here. Okay, so this is how our first screw displacement looks like. If we want to write it completely, then we can just expand this rxi once, rx alpha I, and I think you are already familiar with this notation by now, where c alpha I is cos alpha I and s alpha I is sin alpha I. Okay, if we, let's say, write this completely, right, so this is 1 0 0 0 0 c alpha I minus s alpha I s alpha I c alpha I. This is the zeros 1 cross 3 vector, and then the translation part ai 0 0 1. Okay, so this is the first one. This is the first one. Okay, now we need to we need to perform scr2 after this scr1, right? Okay, so this scr2, as I have said, this scr2 will take us from this intermediate frame m to frame I plus 1. Okay, so this will be written like this. Okay, so uh, similar to this. Okay, so this is basically your translation of di along zi and rotation of theta I about zi. Okay, so what does this mean for us in terms of real math? So this is the second screw displacement, and the homogeneous transformation matrix for this looks like, since this is a rotation about z, okay, so we use the fundamental rotation matrix for the rotation about z by theta I, the constants, and now the displacement is along z, right, by di. So this is 0 0 di. Okay, so this is the uh, second screw rotation matrix, okay, the second screw displacement, and if we just expand it, it will come to be like this: c theta I 0 0 1 0 0. Okay, now to get the final you know yeah, Moro, you want to say something?
Yes, yes, sir. Sir, can you explain that RX alpha I, like, will you be elaborate, sir? Like,
How do we get this?
yeah, yes, sir, yes, sir.
we've already discussed that in the previous week, but okay, like if
If
you
it's a short in short, yes.
yeah, like there is no short if I have to explain. Right. Okay, I will just try to keep it brief. Okay, so
Okay.
if you align your axes, okay, such that you are only considering rotation about x. Okay, so what you're considering is that your rotation axis is coming out of this plane. Okay, the x axis. Okay, so what will be the other two axes in that case? Okay, it will be the y here and z here. Agreed?
Yes,
Agreed.
sir.
Right. So now, if you take now any vector like that will be affected when you rotate about x will be the vector that will be in the plane zy. Okay, because
Okay.
every other vector will just be perpendicular to it, parallel to x, so it won't be affected by rotation, right?
Okay.
So now if you take this vector, let's say v, okay, it has some components and we
Okay.
will call it y1 z1. Okay,
Okay.
and we rotate it by, let's say, angle theta, right?
Okay, sir.
And then the new components are let's say y2 and z2, right?
Okay, sir.
So if the initial components uh, okay, one second. If the initial components of v, okay, let's say I'll call this I, okay, for initial, were x1, y1 and z1,
Okay.
and the final components of v would be what? x1, y2
Yeah.
and z2,
Yeah.
right?
Okay, sir.
Okay, now we'll come to how we get x2 and y2, but the idea is that the x coordinate will not change.
Okay, the X plane is same actually.
Yeah, because we are rotating about x, right? So
So,
the only change
okay,
will be
okay.
in the zy plane.
Hmm.
Okay, now we'll
Okay, sir.
see how, now this is a geometry problem that you have already solved in your 11th and 12th standard, right? That if this angle is theta, okay,
Okay, sir. Okay,
and
sir.
initially there are y1 z1 and finally they are y2 z2, how are
Okay.
they related? Okay, so you'll just find that they are related like this.
Consider by yes, sir.
Yeah, z1 and z2 is your sine theta y1 plus cos
Sorry.
theta z1. Okay,
Yes. Yes, yes.
right? So now if I write, this x1 y2 z2, that is the final coordinates in
Okay.
matrix form. Okay, so this is what x1, this is c theta y1 minus s theta z1,
Yes.
right? And this is s theta plus c theta z1.
See the
Now
one.
you see
Okay.
this particular set of equations, it is linear in x1 y1 and z1, right? So we can break it into a matrix vector product, okay, like this, where the initial vector, the initial coordinates is our vector, and
Okay.
what will be the matrix for this? It will be this matrix, and this is what we call the fundamental rotation matrix about x for a rotation by an angle of theta.
Okay, okay, sir.
You can derive similar matrices for fundamental rotation about y or z, okay, using the similar same principle.
Okay.
Okay, so yeah, let us come back to the dh parameters and
Okay,
screw
sir.
displacements, right? So we have used it to define the transformation matrices, okay, from frame I to m, and then from frame m to I plus 1, right? Now we know that we can compose these, and to compose these we can directly multiply these two matrices, because that is the operation that is
Okay.
defined on these two. Okay, so
Okay.
if we multiply these, right, what we will get is, so the resulting matrix, okay, if we multiply these two matrices that we have written here, right? I'm not going to do this because it will be just a waste of time
Okay,
for
okay,
you.
sir. Thank
Okay,
you, sir.
but if you multiply this and this matrix, you will get the final transformation matrix between frame I plus 1 and I. Okay, so
Okay.
yeah, that's fine. So this is basically why we've defined the h parameters. Okay, because now once if you multiply these and you have a final expression for ti I plus 1, then you can just identify these parameters. Okay, we just identify these four parameters for every joint pair,
Okay.
and then we just use this final result, okay, that is already in terms of those four parameters, and we just plug those parameters and get the transformation matrix. And
Okay.
the final form of this matrix you can get in any book. Okay, you can get in JJ Craig, you can get in Schilling, or like any robotics book you want to find. So that is the reason why we use DH parameters, right? It makes our life easier, it makes standardizing the solution method easier. So any doubt in
No,
this?
sir. No, sir.
Yeah. Okay. Anybody else? Does they have any doubt? Okay. I'm assuming there are none. So what I'm going to do is I'm going to start with a very simple example of a 2R manipulator, and we'll just identify DH parameters for a 2R manipulator. Okay. And then we'll solve some more other problems that we can just cook on the go. Okay, so what I claim is that this uh, you know multi-body system, okay, this has three links. One is your link 0, that is the ground link, okay, and that is like fixed to the ground, that is ground. Then between ground and link 1 there is a revolute joint, and between link 1 and link 2 there is another revolute joint, and both the revolute joints are in the same plane. Okay, they are out of the plane of the paper, they are parallel. Okay, I also define one link 3, right? I just define it because I know it will make my life easier, but I'll explain why I did that, you know, when I'm making the DH table. So now we have this multi-body system where all the links are rigid and connected through joints. So the first step to identify DH notation, DH parameters, is to assign DH notation to any system. In this particular case, there are two joints. So basically there will be two joint axes. So at this joint coming out of the plane will be your Z0 and Z1, right? Because why Z0? Because this is how we have defined everything. This is your X0, Y0 and Z0 coming out, and between link 0, right, between link 0 and link 1 we assign Z1. Okay, similarly between link 1 and link 2, okay, we assign Z2. Similarly, between link 2 and 3, okay, we will assign z3 just as at this point, okay, because these are frames, we can do that. Okay, we can say that there is no relative motion between link 2 and 3, or there is a fixed joint between link 2 and 3. Okay, so we can, assign a joint frame wherever we want. Okay, but usually we assign them at where the actual motion is. Okay, and then we assign the x axis. So again, from z1 to z2, okay, the common perpendicular between z1 to z2 is where we assign x1. Okay, and the common perpendicular between z2 and z3 is where we assign x2. Okay, now this is the reason why I had defined this link 3, and I was defining the frame at this joint so that I could define the x2. Okay, now where does the x for link 3 go? It goes along the same axis as x2. Okay, so the frame x2, basically the frame 2 and frame 3 will be oriented, will have the same orientation always. They will just be a distance apart from each other. Okay, and let's say the link lengths for each of them are L1 and L2. Okay, so if we already have Z and X, then because we know we are only going to use right-handed coordinate system, we automatically have our y, right? We can just do Z cross X to get the direction for y. So I'm not going to represent that in this one, but like if you just wanted to, then since Z is out of the plane, X is from Z1 to Z2, then you can just take the cross product and get that the direction of y1 will be along here, right? Similarly for frame 2 and frame 3. But I'm not going to do that, otherwise it will make this whole diagram really messy, more messy than it already is. Okay, now we have assigned joint frames according to DH notations. What we'll do now is we'll make a table that we call the DH table. Okay, and in this table we will identify these DH parameters. This will be your AI, alpha I, di and theta I. And how many links do we have? Okay, we have link 0, okay, I'll just write 0, 1, 2, 3. Okay, these refer to the links, these numbers. Okay, so now it is simply a matter of identifying the AI for, let's say, the 0th frame, right? So what was the definition of AI if we were to go there, right? Let's recall it. So AI was the distance between Zi and Zi plus 1 along xi, right? So along x0, distance between z0 and z1, okay, z0 and z1, they are coincident, so AI is 0. Okay, now twist also, along x0, the twist, the rotation, relative rotation between z0 and z1, that also is 0. Okay, now for di, guys, since this Google call will end in 15 minutes, what I'll do is I'll make another Google Meet link and share it in the chat, right? And once this meeting ends, we can just all join the new meeting. Okay, not now, when this one ends. So I'll just share this link. Yeah. Okay. Yeah, back to this again. So for di, it is distance between xi and xi plus 1 about zi. Okay, so for link 0, distance between x0 and x1 about z1. Okay, so again this is 0, right? Because there is no distance between x0 and x1. They're both at the same origin. And for joint angle, okay, it is the angle between xi and xi plus 1 about zi. Okay, so if you're talking about link 0, then it is between x0 and x1 about z1, about z0, right? Or you can just, even do in this case about z1. It would not have changed anything, because this angle between x0 to x1, let us call it theta 1. Okay, so this parameter is our theta 1. Okay, so now we have started filling out the dh table. Now we'll do the same thing for link 2. Okay, if you do this for link 2, this will be L1. If you cannot identify how this will be L1, please tell me right now. Okay, I'm assuming all of you are comfortable now. Yeah, and these entries will be like this. This will be L2, 0, 0, 0. And like there will be nothing for 3, because there is no frame 4 that we have defined. Even this frame 3 we had defined to be able to define x2. Okay, so there is no transformation between frame 2 to 3, right? Yeah, the only transformation from frame 2 to 3 is L2. Okay, starting from 2, but after 3 there is none. That is why there are all zeros. Okay, so now what we do is we start with T01. We use the formulae that we have. Okay, not this. Yeah, we use.
So which angle you have considered that theta one, theta two?
Oh yeah, sorry. Theta 2. Okay, theta. What is theta? It is angle between zi and zi plus 1. Right.
Yeah, that
So
I understood. Like yes.
yeah, yeah. So it is between x1
Okay.
and x2.
Okay.
Okay. So this angle is theta 2. Okay. So this is why
Yeah.
we did not take from the ground, because according to convention, wait. Yeah, because according to convention, we want to go from just xi to xi plus 1. Okay. So yeah, this is the DH table for a simple 2R manipulator. Okay, and now if you just follow these same procedures step by step for every manipulator, okay, then you can just arrive, or you can solve the problems. Just keep one thing in mind, like these notations to solve the problems. If to, like, I don't know, be consistent with the notation that you use. Okay, either use a notation that sir is using in class, or use a notation that you find in a book, or you make up your own notation. I don't know. Just be consistent with what you choose. Um, okay. So what we will do is, James, you have some problems to discuss, right?
Yeah. There are some quite few problems, like 5 to 6. I think 1 hour time will be good. Or if you want to wind up now, then I can continue with my. Am I audible?
Yeah, yeah, you're audible. Yeah. So what?
Okay, I think I can continue with the problems. If you, I think 1 hour is not enough, so you can start. I think.
Yeah. Like I've already made the meeting link, so I think we can shift there right now, right? Because otherwise the
No,
meeting
I
will.
think no. The thing is, what do you say? Like, if we start now, I think the link is for only 1 hour, right?
Yeah, that's why. Like it will end in 8 minutes.
Yeah. So in 8 minutes, I can cover one problem. Then, what do you say?
Okay. Yeah.
Then we can start on X, Y, and Z axis. Okay, all together.
Then I'll
So
just stop
if
sharing
point P
this
in a
screen.
frame A is given as
Uh,
101, find the coordinate in frame B. Okay. So how we start is
yeah. Yeah.
AP
And then from my end,
means
I
the
will
point
just.
in frame A is given as 101, or you can write in a vector form. Okay. In calculation, we can do in a vector form, which is nothing 101 like this. And rotation. Okay, rotation is about y-axis by 60 degree. So how do you write this? So after rotation, you can write as AP and apply the rotation. Something is happening with my, yeah, that. Oh, what's wrong? A, B, and BP. Something is really troubling me. Sorry for that. Okay, I think what happens here. Okay, so it is clear, right? If anyone has a question, they can raise the question. So the next is, how do you proceed forward? This R of A, B, what is it? It's about y-axis by 60 degree. Wait, just give me a second. I think it's very 60 degree about y-axis, and then BP. Clear? So now we have to find BP. BP will be, we'll ignore this part, okay, and write only R. And everything will write only R. We'll take R on the other side, it will be R inverse of AP. Yeah, R inverse of AP. And then since this is a orthonormal matrix where R inverse is equal to R transpose, this is the best part about the orthonormal matrix where each column, all the columns of the matrices are perpendicular to one another. So instead of inverting the matrix, you can just transpose it. Okay. So this R, how do you write this R? This R is cos of theta 0, sine of theta 0, 1, 0, minus sine of theta 0, cos of theta. Okay. And then AP. AP is 1, 0, 1. Clear? So which we can further write cos of 60, 0, sine of 60, 0, 1, 0, minus sine of 60 degree 0, 1, and then 1, 0, 1. So this is simple maths, okay, simple maths, the basic which everyone knows. 0 0.5, 0, 0 0.866. One thing we should be very clear here is minus sign appears here. Okay, the minus sign appears here, not here. They should be very careful. In the jet, it appears around here. or I mean, in Z it appears around here. In X it appears around here, but on the bottom left, okay, bottom left corner it appears in negative sign. Be careful. Simple mistakes are made some most of the time. Sign 60. I think I made a mistake here. What is it? This, it should be cos 60. Okay, cos 60, 0.5. If you multiply this matrix, then how much you got? This you add up. Simple. 0.5 plus 0.86. How much you got? 1 1.3660, and this one leads to 0.366. Okay, you got some value. So this value is nothing but this is AP. AP equal to this, which is you can write in the coordinate form, not in the vector form. If you are asked what is the coordinate, and if you write in the vector form, then the examiner, whoever is grading it, can give you a negative mark. Okay. So this is AP. So the question says what is, oh, I think this is BP, sorry. This is BP. Means the frame which was rotated by 60 degree about y-axis of fixed frame A. Okay. Then the point B, which is 101 in the frame A. What is the corresponding point in the frame B? So how do we verify this, whether it's correct or wrong? It's a simple thing. Like, it's just rotation. The length remain unchanged, okay? So what you can do is the length remain unchanged, and if you take norm means the distance from the origin of that point, AP, okay, and the point BP. If you take a distance of this point A and point B from the origin, then it should be same. So then AP, if you take a norm of the point AP from the norm is distance, this I think 1 plus 1. Okay, it's root 2, which leads to 1.414. Again, here I think in the same way you can take the norm of this point BP from the origin, then this will lead to approximately the same value, 1.999 something, then 1.414. Got it? I think this ends. This is the
Also,
first part of the
just
question.
just a quick correction.
So
The third coordinate will be minus 0.366.
minus, where is it?
On
Oh,
the
yeah,
second
sorry,
column.
sorry.
Yeah.
Yeah, sorry, sorry. Okay, thank you, Nimesh. So I think this should do the first. Hello,
Yeah.
am I audible?
Yes. Clearly.
Okay.
James, I'm sorry, you'll have to unmute yourself. I mistakenly muted you. Yeah,
Okay.
yeah.
Okay, cool. So should we start the second question? Nimesh?
I think you can, yeah. Like if people want to join, they have the link. They'll just keep coming. I'll keep admitting.
Okay, because I see very less people here, so
Yeah.
a lot of waiting.
Okay.
Okay, the second part, the second question is given here. A frame B is rotated by 30 degree about y-axis of the reference frame A and translated by unit 101. Okay, in the x, y, and z direction respectively. The coordinate of the point in frame A is 101. Find its coordinate in frame B. Okay, here we are going to use not the rotation matrix, but the combination of the rotation and the translation matrix, which leads to the 4 by 4 homogeneous matrix, which is not orthonormal. And the transformation is not equal to the inverse. So you can make a mistake. Okay, when it says the inverse of the transformation, if you, no, sorry, inverse of the transformation matrix, if you transpose it, then you might get it wrong. Okay, so I think we're gonna start the problem. Yeah. So rotation is about 30 degree above y-axis of A. Okay, I can make it a unit vector y. Okay, and the the transformation. How should I put? I should write del p. Yeah, the transformation and the position of point A looks the same here. Okay, so what does it leads to? Let's see. So the translation, I'll write it like this. Given, this is given. And the point in the frame A. Okay, in frame A means this is the frame A. You write like this in according to Craig's convention, and the point this is AP, which is nothing but 101 in vector form. So the point A is this. So we have a frame A, and then it's rotated by 30 degree about the y of A, and then translated by this vector. Okay, means along x 1, along y 0, and along z 1. Then find its coordinate in frame B. So you know the transformation the transformation matrix, which is an assemblage of the rotation and the translation, is written as T equal to, like, from T of A to from A, T of B to A is written as rotation of B to A 0 0 0 1 and del P. This way you write. Fine. Okay. So this rotation matrix, it's according to which axis you are rotated, like along Y, along Z, or along X. And this is the translation. Okay. And this is just 0. And what do you call this? This is, I think, the scaling factor, which is not of much importance here. Then how do you represent the transformation? We can write AP equal to T A of B BP. So the problem lies here is This is 4 by 4 matrix, okay? And this is 3 by 1. Again, 3 by 1. So what we add is another 1 so that we can multiply it 4 by 1. It becomes 4 by 1, and here also we add one scalar 1, it becomes 4 by 1. Now I think we can do the multiplication. And once again, T inverse is not equal to T transpose. Clear? So what is given in the question? It's given in the question AP. AP is given. We have to find BP. So we have to invert this T matrix. So BP 1 can be written as T of B to A inverse AP and 1 vector. So how do we get this value? The inverse of the transformation matrix, which is not equal to the transpose of the matrix. So this is, I think, well derived in the, I think, week 2 lecture, which I'm not gonna do the derivation here, but I'll just write the formula. How does it look like? It looks like, let's say, T of B to A is given as R B to A 0, 0, 0, 1 del P. And then T of B to A inverse is R A to B inverse R A B to A, sorry, inverse of del P minus. If you do this operation, then you'll get exactly the required inverse of the matrix. This, okay, we get exactly. So now you have to find, first you have to find the inverse, okay, the rotation R matrix, and then you have to get it the inverse and then multiply here, and you'll get this as a 3 by 1 matrix or 3 by 1 vector, 3 by 3 matrix. So let's find the matrix R A B to A, sorry. So this is nothing but rotation of along Y by 30 degree. Okay. So this is, I think we should directly write, no need to write the formula. So it's cos 30, 0, sine 30, 0, 1, 0, minus sine of 30, 0, cos of 30. Yeah. So Nimesh, I think since the session ended, I think none of them have joined the session. Okay, none of
Like
them, because
two of them have,
I
like
think they forgot to save. I think they forgot to save the link. I
no,
believe so.
it's like usually those students they just attend the initial few minutes and then they do not join in the second one.
Okay, fine,
Yeah,
but it's okay. I have no issue. Yeah, so I should continue,
yeah.
right? So yeah, so the rotation matrix is now it looks like this. Now we need to get this rotation matrix and multiply it with this to get this negative value in the front. So R inverse looks like 0.8660 minus 0.5010, 0.50, 0.866. So the first part is done. This part is done. Now we're left with this. The second part should be R, the rotation matrix. I'll write only the R, okay. R transpose of del P. So this is R transpose or R inverse, say. And what do we have? This del P. Del P is this. I need minus, okay. So fine. Now I think we can construct the required matrix, which is nothing but the inverse, which I need R inverse, which is 0.8660 minus 0.5, 0.866, and then this, oh, sorry, then this, right? Minus 0.3660 minus 1.366, right? 0, 0. This is the required transformation matrix, inverse of the transformation matrix. Yeah, so we'll do the main operation, which we needed. This operation, I think, this operation we're gonna do. So these metrics I'll just write it over here, okay? I think, no, I think I'll just copy this thing, whole thing. This times the position vector of A would in the frame, what is it? In the frame, yeah, A. Point position vector of the point P in the frame A. This will lead to what is one very beautiful thing is this will lead to 0, 0, 0. Yeah. So the position vector of the point in frame B is 0, 0, 0, or its coordinate is 0, 0, 0. What does it mean? Like, what's happening here? What we can conclude is, see, if you go back in the question, I think if you're smart enough or if you have practiced a lot, then we can conclude that, see, the rotation, the transformation, okay, and the position vector of the point are same. Means the frame here, the point P was here before, and the frame, this whole frame is translated here. Obviously, then of course the new frame has brought in this position, so this point will be of 0 vector. This vector will be 0. This coordinate will be 0, 0, 0. That is, it means that. Okay, so this ends question number 2. 3. So before Nimesh has discussed planar mechanism, and then in that we'll just add one just simple one degree of freedom more, and then we can discuss it, the DS parameter, how you assign the DS parameter according to the Craig convention. And one thing we should be clear here is there's no fixed rule. Some books follow some convention. Okay, in Craig, we're following the Craig's convention and we're following the Craig's rule. Okay, so stuck to one notation or one convention from any book and keep working on that. Don't get mixed up. Because if you follow one convention, then the matrix multiplication might be AB, and then if another convention, it might be BA, something happens that you will come to know when you go further. So here, what's happening here? This is 3 degree of freedom RRR manipulator, revolute, revolute, revolute. So what's happening here is the first rotation is the jet is in this direction. Okay, means the rotation in this direction. Means because of this rotation, this whole system will be moved out of the plane of the paper. So this rotation by θ1 will take you to any plane of the paper. Like I have a one joint here, one joint here. Okay. If I move like this, it's taking to some plane. If I'm here like this, my hand, it's in some plane. If I move like this, it's taking in some other plane. That's what θ1 is doing. θ2 and 3. This corresponds to the θ2 is pointing out of the plane of the paper. No, I mean this jet. Okay, we'll continue and we'll figure out which jet corresponds here. So the jet pointing in this direction, this jet, whatever jets will be, it's pointing out of the plane of the paper, and same here, out of plane of paper. And this rotation is responsible for moving in this plane and on this plane. So how do we do the Diels parameter convention? Okay, and one thing we should know is, if I ask you to draw the x, y, and z axis, somebody will draw like this: x, y, and z. Okay, this is a right-hand screw rule. Am I right? No, I think I'm not right. Oh, yeah, I'm right. Yeah. So it might not be here. It depends on how you define the zero frame. Okay. So the zero frame you can define according to your convenience. So what is more convenient to us? Let's see. Okay. So here one rotation is so let's in the same place here. Let's draw another frame, another axis, which is Z0. And then this can be Z1. Remember, rotation and translation are along all the z axis, okay? Z axis. So if I met the Z0 here, Z1 will be obviously. If I made the Z0 here, Z1 will be obviously here. So that it can mark the change in angle θ1 here, or θ dot. So let's not talk about θ dot, we'll just mark θ1. Fine. So, and then this can be what? This can be Z2, Z3. So we begin. Then we have Z0 and Z1. As I think Mimesis said that the X should be normal to both the jet and the next jet. So what we can draw here is, we can draw the x0 here. Okay, I think I'll draw a little bit inside. Okay, and I'm gonna say why I'm gonna draw it inside. I'll pull this a little bit inside. Yeah. So this is x0. Then we have here z0, x0, and z1. Let's say initially we have x1 coincident with x0. If you rotate by angle theta, then obviously there will be an angle between x0 and x1. That's why I draw a little bit inside so that you can visualize it more clearly. So now because of the rotation, x1 comes out here. And remember, this is not coming out of the plane of the paper, okay? Remember, this is how you visualize. There is no rule to learn how to visualize, okay? It depends on any question, no question, right?
Yes, one question. Like theta one is that angle between z0 and x0, na, sir?
No. Rotation is about x0, z0, and theta 1. Wait, first I'll remove this, okay? Wait. I know your question. Yeah, this theta 1 is here. Okay, you got it? Rotation is
Yeah.
about z-axis, but the angle is reflected where? In the angle between x0 and x1. Clear? Uh, is it clear or not? I
Yeah,
can
it's
explain you once again.
yeah, it's clear actually. I understood. Actually, I'm confused
Yeah,
between Z0 and Z1. That's theta one.
yeah. See, let's say this white, the white pencil is z, okay, and the two pencil. If you rotate it, and this will separate, okay, this will get separated. So this is theta. Yeah. So we don't usually write here. We write theta where in the direction of the rotation. Fine. So I think we should start writing before it gets messy. Okay. So what is angle between the two jet? A. And then distance between the two jet is A. Angle between the two jet will be alpha. Distance between the two x d and theta. I think in grade you write like this: I minus one, I minus one, I and I. Right? So angle distance between Z0 and Z1 should be it's 0. Angle also 0. Between the two x, I think it is 0. And then angle is theta 1. Theta 1 is drawn here, is written here. Next we start. Are we out of time? No, I think we're on time. So next from frame 1 and 2, from 0 to 1, from 1 and 2. 1, x1 is already here, z1 is here, and then z2 is here. Okay, then see, z1 is here, z2 is here, x1 here. So then the other jet should be along the sorry, the other x should be common perpendicular, right? So x2 comes here. Got it? So from frame 1 and 2, the distance between the two jet is still 0, right? Z1, Z1 is here, and Z2 is here. Distance is still 0, it's intersecting. So it's 0. Yeah. And then angle between the two jet. Yeah, angle between the two jet, how much? 90 degree, because of course we rotated 90 degree. It's negative 90 or positive 90. I think it's positive 90. And distance between the two x1 and x2 is intersecting, so it's 0. Then angle. Okay, the angle which before you're confused, right? So rotation is about here. Okay, it's about here. Am, am I drawing it right? Yeah, it's about here. So the angle is reflected here. So it's theta 2. Theta 2 is reflected here. Theta 2. And then I think the second row is done. The third row will be jet is pointing out of the plane of the paper. Is pointing out of the plane of the paper, and the next x3 will be pointing along the length x3. Okay, so see, this is L2. Okay, the length which we won't be using. Okay, because we are going to write the convention only till the third frame. this was the direction of x2, right? Was the direction of x2 before. So whatever angle you see here, which because of this rotation by angle 3, theta 3, it will be reflected here, theta 3. So it's L1, this L1 between Z2 and Z3, the distance is L1, angle is parallel, so 0. Distance between the two x2 and x3, x2 and x3 are, I think, is intersecting, so the angle, the distance still remains 0, and then the angle between the two x, which x2 and x3. This is the x2 direction, and in the x3 direction, rotation is above z3 axis, so it's, oh, sorry, theta 3. I think you are done. I think we're done with the DH parameter convention. So we don't have, yeah. So I think we can continue further. Okay, how to write the transformation matrix. Before in the previous lecture, Nimesh has write about the compound transformation matrix, which will take you consider the rotation and the transformation. Okay, first translate, then rotate. No, first rotate about z, and then translate about z. Rotate about x. Is it? Am I right? No. I think rotation x, translation x, rotation z, and translation z. Yeah. That was the compound transformation matrix which Nimes has covered. Okay, that will be used everywhere, not a simple one. So instead of writing cos theta, we can write c theta. Okay, stands for S stands for sine 0 a. Sine theta, cos alpha, cos theta, cos alpha. We won't do all, for all the rows. Okay, we will do only for one row, and I'll write you the solution, and you can practice it. And I'm gonna explain to you how you're gonna verify. Okay, S stands for sine, C stands for cos, stand for cos, C alpha. Oh, sorry, I think this should be cos theta, sine alpha, cos alpha, cos alpha, D 0 0 0 0. See, if you look here, okay, this still looks like the transformation matrix we discussed before. Okay, this is the translation part, and this is the rotation part. So of course, and this is the, I think, amplification. This stands for amplification, and then this is the rotation matrix part. Okay, this will be orthonormal, obviously. So let's write for T01. Okay, so if you go back, we don't have any value. All the values are 0. A0, alpha 0, D0. Okay, and except theta, we have, I think the only value here available is theta. But be careful, okay? Don't, this might lead to 0. You think that everything is 0, this will lead to 0. No, we have cos, okay? So cos of theta, yeah. So we have cos theta 1 minus sine theta 1, 0, 0. Okay, A0, log A0, everything 0. Then S sine theta 1 cos theta 1. Sine theta 1, why? Yes. Cos alpha, cos 0, cos 0. So you have only cos available here. Yeah, right. The first part is done. Okay, this pretty much look like what we have done with the Rx. This looks like Rx, right? No, sorry, RZ. Yeah. Why it looks like RZ is, yeah, of course, it was rotating along Z. But in the second transformation, okay, which is T 2 to 1, it won't look like this anymore. Like it won't be neither Rx, Ry, or Rz, because there is another rotation which involves alpha. Okay, another rotation which involves the angle alpha, so it won't look like this. How it will look like? Cos of what we have, theta 2, right? And sine of theta 2, 0, 0, 0, of course 0, 0, and what we have here? Sine alpha, sine of how much? Sine of 90 degree, sine of 90. So minus 1. See, it's diverting from our previous basic rotation matrix, but it's not, okay, it's some permutation is going on. Yeah, this is the T2 to 1. And in T3 to 2, again, I think without much calculation, you can say that from frame 2 to 3, it's simple rotation along the z axis. Okay, so by how much? By angle of theta 3. Yes, 3 c theta 3. I think a lot of problems with my writing pad. I don't know what happened. This is the first time I'm using this. Sorry for that. Yeah, so if you multiply everything this, okay, you can get the compound transformation matrix, which is nothing but taking from frame 0 to 3, which is 0 to 1, 1 to 0. Sorry, you don't say like that, okay, it's 2 to 1, 3 to 2. If you multiply, then I think I'll write only the answer C1, C2, 3. Okay, I'll explain you what is C2, 3, okay. Minus C1, S2, 3. S1, LC1, C2. S1, C2, 3. Minus S1, S2, 3. You write this way, okay, don't write a very lengthy cos theta, sine theta. It will cover the whole page of your book. So this is the best way. This is how it's written in gray in most of the books. Well, yeah, this is what you got. Here I'm gonna take some space of here. What's happening here? C23 means cos of theta 2 plus theta 3. We write this way. Okay. Same with sine. C1 means cos of theta 1. Right? S1 means sine of theta 1. So you can see anything. S23, sine of theta 2 plus theta 3. So here, how do you validate this? How do you think that it is right? Okay, there's no way. You have to solve it again and again, and if all the answers are correct, then you can say it's correct. But in one go, how do you say that is correct? This should be 0, no doubt, okay? Because this is a homogeneous 4x4 transformation matrix. This should be 1. You cannot change this. This is scaling factor. If you change this value, something goes wrong, amplify it. And this part, this should be orthonormal. And you know what? This part, what's going on here? This, if I go back, I think if I go back in the previous lecture, yeah, this del P, which is the translation. Okay. So this part gives you the position of what? Frame 2. Sorry, frame 3. Okay, it gives you the position of frame 3. Where is this point in space? Okay, where is this point in space? It's given by the last column. Okay, the last column of your transformation matrix is given by that. Okay, so if you want to find this point P, which I thought of finding before, okay, but because of we have limited time, we didn't. So how do you find point P? Then you write the DH of that, right? 3 to 4. What is it? L2 0 0 theta 4. There is no theta 4. Why? Because it's just translation going on. This frame will be translated here, okay, with no rotation. So you just write 0. And if you write the transformation matrix of the last frame, we call it n effector. or an effector, or in humanoid robot, you can call it gripper. Then which should be 4 to 3. What it would look like is nothing but no rotation. Oh, sorry. 1, then L2. I think it's L2. Is it L2? Yeah, L2, 0, 0. Why this is happening here? Because remember, the translation is along X, okay? The translation is along X. So we have only the X displacement, and the rest of the R part is an identity matrix. It means no rotation is going on here. So if you take this and if you multiply it here, 3 to 4, and this final, that's the row final column, including excluding this, will give you the position vector of what of point P. That can be your homework. Yeah, I think done. We are left with just 2 questions. I think this parameter convention. Yeah, this one. This is this looks very complex. Okay, even I find it very complex, but it's not complex. First, it looks complex, but it's very easy. Okay, you might think that you have to uh, do what you call datum or base, and it's very confusing how to assign the frame. Yeah. So here, what is this? This is 3 DOF, degree of freedom, P manipulator. Prismatic, prismatic, prismatic. The translation, and the translation, right? Yeah. So how do we start? We can start with from here. We can start it from here or from here. Anywhere is fine. Okay. This is all about design. Okay. All about design. So you can start, let's say, because we are dealing with the kinematics, so it's just displacement. We don't care how many support we have. Okay. So don't get confused with that. Okay. The design engineer and the factory guys will handle the design. Okay. We're not to handle that, such things. So we have assigned here what? X, X0 here, Z0 here. Why Z here? Because it's translation going on. All the translation and rotation should be along Z. Okay, and I will assign another Z here, Z1. Okay, and then X1 comes here. Okay, X1 comes here. It makes sense, right? Now we have the translation. So this given as D1. D1 is nothing, but it's not a fixed value, D1. What does D1 means? D1 means the distance between any X. So between X0 and X1, the distance is D1. Okay. It should end somewhere here, but this is how the book gives. Okay. This is how everyone, this convention, and everyone understands by this notation. So we write the H parameter 0 to 1, 1 to 2, 2 to 3. Yeah. So A alpha D theta. Sorry. D theta. Remember, this theta is not the variable. The variable here only is D. This is prismatic. Be careful. Okay. So we have the angle between the two Z. How much it is? 0. 0. Distance is 0. And distance between the two X. How much? D1. Don't say that D is a measure from here till here. Okay. It doesn't matter. Okay. This is just where the book gives. Okay. Don't get confused with this. And theta? Angle between two X? 0. Fine. So it's now translating. When this translates, when these body translate, everything translates. Okay, these everything. Okay, this part, this part, this part, this part is same body. So when it translates along this, it moves. I think we are smart enough to understand the basic mechanism of this drawing. Okay, this figure. Then next, what shall we do next? So we have the next. This is, I would say, this is frame 0. Okay, I will write here. This is frame 1. This is 2. Frame 2, not frame, sorry, link. So why I'm writing is this is where I'm gonna assign my frame. Okay. So translation is along where? Along Z2. And X will be pointing where? This direction. X2. So now it makes sense, right? See, it depends on how much you practice, okay? So we have the previous X1 here, now the new X2 here, which is common normal. And this D2, what does D2 represent? D2 represents the distance between the previous X and the new X, which is D2. So I think now we can write 0, angle between the two X, angle between the two X, between the two X, right? Which is, no, sorry. I'm mistaken. So, yeah, sorry, angle between the two Z1 here, Z2 here. So you rotate it. First, you rotate along X1. Okay. If you rotate along X1, the new Z2 will appear here. So then what do we have? We have rotation is, I think, counterclockwise. So it should be, yeah, I think I'm right. Now I'm right. Sorry for the mistake. And then you have translation. Translation along what? Along Z, which is the distance between the two X, X1, X2, which would be the variable of our interest is T2. And then we have another rotation. What? Rotation along Z2. Okay. By along Z2, how much? By 90 degree. And it makes the angle between X1 and X2, which this angle. This is direction of the X1 and this is the X2, which is 90 degree. Yeah, I think now we're correct. I think in the right direction. And the last transformation. In the last transformation, what do we have? We have our Z should be pointing in this direction, Z3. And what do we do with X? With the X, we can just leave it like this, X3, right? So now D3 represents what? The distance between the two axes. So this will look like 90. Yeah. Why 90? I'm rotating. This Z by this Z along X2 by 90 degree. And then the variable is here and then 0. No rotation. The angle between the two X is 0. Angle between the two Z, which is Z2 and Z3 is 90. I think we're done with the DS parameter convention, right? Notation, assignment of DS parameter and the frame. So any question here? Okay, let's assume that there's no question. Then we're left with the last question. Yeah, so do the frame assignment. Z0 points in this direction, X0 is here. So, oh, okay, wait. Before I start, I think this is still 3 DOF, and then what? We have prismatic here, we have rotary here, and then is it rotary? Yeah, prismatic here, and then another prismatic here. Okay, the PRP. I think it's P. The P rotation and translation. I think this is 4 degree of freedom, not 3. Prismatic, rotation, then translation, and then another translation. Yeah, right. So we can make it fast. I think we're out of time. 2, 2, 3. You might ask why we're doing only till the uh, third frame. Okay, not the fourth frame, the third frame. Why we're considering that if it is like in the previous case. Okay, this is to do with the kinematics because our goal is not to find the position, but our goal is to find the velocity and all that we'll deal later. Alpha A D theta. So yeah, so Z will should point in this direction, Z1, then X can be still here, X1. Then makes the distance between the two X, which is the variable, and all the remaining thing remain unchanged. No, nothing is changed between the two frame except the relative distance. So I think all the part remains 0. Next can be rotation. So rotation, what rotation is going on? Okay, we can Z2, yeah. And where do you, this is Z2. Z2 is in this direction because we're going to rotate this thing, okay. This is fixed. We're going to rotate all this thing along where? Along this Z2 by theta 2, which is shown here. Yeah, so where do we assign the next X? X2 will be common normal, right? X2. Yeah. Then between the two jet, it's minus 90. Am I right? Minus 90. Yes, minus 90. Z1 and Z2. And then the variable which of our interest, L2, is here. Means the distance between, look over here, it looks like the distance between Z and something which we don't know, okay. But actually, this and both are in the same plane, so this is same as this, fine, which is L2. L2 will be here, and is I think L2 is L2. Yeah, L2 is often it's not of our concern now. Okay, I think. Yeah, I think I made a mistake. Sorry. So yeah, Z1 was here. Next Z2 can be here, and then we have X2 here. Why? Before rotation, when theta, remember theta, which theta was it? Theta 2, right? Theta 2, yeah. Theta 2, if theta 2 is still 0, then x1 and x2 will coincide. Fine, I think I'm making it right. Yeah. So, does it look like this changes here? Yeah, from 1 to 2. So we have x1 and x2. Yeah. Z1 and Z1 and Z2, we have how much? Minus 90 degree. And then everything should be 0. And then the rotation, the variable should be theta 2. Yeah, right. We're on track. we have here Z2
Why
here.
is it minus 90? 1 to 2 alpha.
Yeah, okay. So this
Both
angle,
are perpendicular, Z1 and Z2. Yeah.
this angle.
Hmm.
You got it? This is how much? It's minus 90, right?
Minus or plus?
Minus. It's clockwise.
So anti-clockwise you'll take positive.
Yeah.
Okay. Thank
Okay, clear? And then we have frame jet. We have frame two, and then now we'll deal with. So one prismatic is done, P, one rotation done, and we have another prismatic here. Okay, so what do we assign here? We can assign here Z3 and X3. So the distance between this X2 and X3 is of L2. Okay, so this is the variable of our interest, L2. Fine. So angle between Z, 0. Distance between Z, 0. Distance between X, L2, angle is 0. P, prismatic is done. I think we are left with the last DH 3 to 4. X2 here, X3 here, Z3 here. So another translation should be along this direction. Along this direction. Yeah, this direction, which should be Z4. So how do you bring about Z4? Z4 should be rotation of Z3 by how much? 90 degree. This is positive 90. Okay, positive 90, right?
Anti-clockwise.
Yeah, anti-clockwise. And distance between the two Z is, I was fast, okay, because I don't have much time, only 1 hour. So like distance between two Z is 0. And then where is the new X? The new X will be here. Okay, X4. Why not here? You can think about. Yeah, the new X4 will be here if D3 is equal to 0. Okay, but D3 has some value, let's say 3. That means this 3 centimeter. Okay, so what you do is you just rotate Z by 90 degree, positive 90, you get Z4, and you have X3 along X3 by 90 degree. And then the translation will be brought about by this variable D3. Okay, then what you have now here, D3 and theta. Okay, what is theta? Yeah, 0, right? 0. Because X4 and X3 and X4 doesn't have any angle, it's 0 angle. So with this, I think we are done. Okay, we're done with the frame assignment and DS parameter. Any question for DOF, prismatic, O3, prismatic, prismatic?